Hello, welcome to this course on the modeling, analysis and estimation of three-phase transmission network. Till the last lecture, we have talked about different matrices to actually accomplish the transposition of transmission lines. In this lecture, we will see that how those concepts can be applied to calculate the impedance matrices of a transposed transmission line. So, to do that, what we will consider is a line. So, let us say I do have a line phase A, phase B, phase C. So, this is let us say phase A, this is phase B, this is phase C. Now, we will also say that this is position 1, this is position 2, this is position 3, and then these phase conductors, they do interchange the positions. For example, then they do interchange the positions. For example, so this phase A comes here in this phase B conductor comes here, phase C conductor goes there, and then phase A comes here, phase B comes here, phase C comes here. Total length, so these distances is 1 up to this is S1. Then from here to here this distance is S2. Then from here to here distance is S3. Now, of course, total length of the line is S. And indeed, this relation holds good, S1 plus S2 plus S3 is equal to S, that indeed holds good. So, then here what is happening? The three phase conductors, phase A, B and C, they do occupy the positions 1, 2 and 3 for a distance of S1. Then phase A goes to position 2, phase B goes to position 3 and phase C goes to position 1 for a length of S2, and then lastly phase A goes to position 3, phase B goes to position 1 and phase C goes to position 2 for the last leg of length of S3. So, then therefore, as you can see, over the total length of S, or each and every phase conductor occupies these three positions for some length. Now, what we will try to do is that we will try to compute that what would be the effective impedance matrix of this entire length, right. So, then therefore, we would be basically trying to compute that what would be the total impedance matrix of the line when these conductors occupy these three positions interchangeably. Now, we know that for length 1, so we say that this is section 1, this is section 2, this is section 3. So, for section 1, that is S1, obviously I can say that V1, 2, 3, that is basically position 1, position 2, position 3, that is of course equal to V A, B, C, that is basically, because in S1 we can say that in S1 I can say that V1, V2, V3 is equal to VA, VB, VC, because phase conductor A occupies the position 1, phase conductor B occupies the position 2, and phase conductor C occupies the position 3. And then similarly in S1 also I can write that I1, I2, I3 is equal to IA, IB, IC, that we can write similarly. And then of course a similar, so then therefore for section 1 S1 V1 2 3 would be equal to VABC. So that I can write down as Z1 2 3 into I1 2 3. So that I can write down as Z1 2 3 into IABC. Now Z1 2 3 is basically a matrix of the impedances, right. So then therefore Z1 2 3 is essentially a matrix of the impedances. So it is given by Z11, Z12, Z13 corresponding to these three positions of conductors. So Z21, Z22, Z23 and Z31, Z32, Z33, right. Now because these positions are essentially corresponding to section 1, what we do is that we also here give another subscript which denotes position. So all these last one they do denote position 1. So this is position 1, position 1, this is position 1. So this is position 1. So Zij, so then therefore the notation Zij hyphen k denotes the impedance Zij corresponding to section k, and this k goes from 1 to 3. So these denotes the section, right. So basically section 1 2 3, and Zij is nothing but Z11, Z12, Z13, etc., etc., etc. So then therefore corresponding to section 1 I can write down the relation VA, VB, VC is equal to Z111, Z121, Z131, IA, IB, IC, right. Now Z11, Z12 is basically the total impedance of the line corresponding to length S1. So how to calculate that? That we will discuss a little later on. For section 2, for section 2 V1 2 3 would be V, if we look at it, for corresponding to position 1 the phase conductor is phase C, corresponding to position 2 phase conductor is phase A, and corresponding to position 3 phase conductor is phase B. So then therefore it would be VCAB, that would be is equal to Z1 2 3. I would say that it is hyphen 2 into I1 2 3. So that means Z1 2 3 2 into ICAB, right. Now what is this notation? This notation is basically, this is nothing but Z1 2 3 matrix corresponding to section 2. So this last two denotes section 2. Now what we do is, now to make it VABC, so what we do is we do multiply, pre-multiplied by R phi inverse, and we have already discussed that what is this matrix. So we are not again repeating this. So VCAB would be is equal to R phi inverse Z1 2 3 2 into ICAB. Now this I can write down as that R phi inverse VCAB is equal to R phi inverse then Z1 2 3 2 into R phi inverse into ICAB. Now we have already seen that what would be the result of R phi inverse into VCAB. Essentially the third row would be shifted to the first position, right. So then therefore, no, sorry, it would be basically the first row would be shifted to the third position, sorry. So it would be basically first row would be shifted to the third position. So it would be VABC, and this, and so, and then of course it will be also IABC, and then it would be Z2 3 1 2, because here also the, now here what will happen, that the first row would be shifted to the third position, and then other one would be basically rotated in the a cyclical manner. So then here I can write it down here V A V B V C. So this we have already basically computed, I mean this we have already computed, we are simply taking the result from our earlier analysis. So we are not doing it again. So it would be essentially Z 2 2 2 Z 2 3 1, sorry 2 3 2 Z 2 1 2 let me write first. So it is be Z 2 2 2. So Z 2 2 2 means that it is basically, so then therefore then it would be Z 3 2 2, then Z 3 3 2, and then Z 3 1 2, and then it would be Z 1 2 2, Z 1 3 2, and Z 1 1 2, right. So now you see that this same matrix can also be interpreted in terms of the positions. So basically let us look at that. How does this matrix correspond to the position? So what I have here position 1, position 2, position 3. So this is position 1, position 2, position 3, and my phase conductors are CAB. So CAB, CAB. So this is for section 2, right. So this is my position, this is my position. position. So you see, so then therefore phase A corresponds to position 2, so then therefore it is Z22 for section 2. Now please note that this Zijk is I can say that Zijk is, I can write it down here more explicitly as that this is basically impedance corresponding to positions ij for section K, right. So Zijk is nothing but impedance correspond to position A, or rather it is actually the element of the impedance matrix correspond to position K. So I should say that it is elements of impedance matrix. Let us write. So it is element of the impedance matrix corresponding to position ij for section K. So this is the case. So with this definition, so then therefore because phase A occupies position 2, so then therefore it would be Z22, and then A is connected to phase B and phase B takes the position 3, so then obviously it is Z23, and then the coupling between phase A and phase C would be essentially the coupling between position 2 and 1, and then similarly here also phase B takes the position 3, and then when it is being coupled with phase A which is in position A, so then it would be Z32, and then it is Z33, and then it is Z31, and so on and so forth. So this is the case. So this is, let us say this is equation 2, and let us say that this is equation 1. Now what happens for section 3? For section 3, V123, now let us see for section 3 what is V123. V123 would be VBCA, 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 VBCA. It would be Z1233, then I123. So it would be Z1233 into IBCA, right. Now what we do? We pre-multiply it by R phi. So then therefore when I do pre-multiply it by R phi, so I get V R phi into VBCA is equal to R phi into Z1233 into IBCA. Again we note that Z1233 is nothing but the Z123 matrix, that is the 3 cross 3 Z123 matrix corresponding to section 3. So we can write it also just to be explicit. So you can see that this is Well, now from this I can write down BCA. Right now, this effect is just the reverse of the effect of pre-multiplying by R phi inverse. So, here the effect would be that the last row, that is basically the third row, will be shifted to the first position. So, then it would be V A B C, and then it would be basically Z 3 1 2. So, it would be 3 1 2 Z 3 1 2 3, then it would be I A B C. Now, one thing I must say, that instead of writing it here Z 1 2 3, I should write it, we should to be on the we should write it as to be on the we should write it as to be, to follow the, to essentially maintain the uniformity of the notation. So, it is this. So, again just that it is, again I should say that Z 1 2 3 matrix corresponding to position 1 or section 1, sorry, corresponding to section 1. Anyway, so here I can say, so then if I do now VA, VB, VC is equal to, so it would be Z 3 3 3, Z 3 3 3, Z, then B is Z 3 1 3, then Z 3 2 3, right, and then it would be Z 1 3 3, Z, then 1 1 1 1 3, and then Z 1 2 3, and then it would be Z 2 3 3, Z 2 1 3, Z 2 2 3. So, it would be I A B C. Now, these also we can again interpret it in this fashion. Let us see that for section 3, the position 1 2 3 is BCA. So, let us see. So, for section 3, the positions 1 2 3 are BCA, 1 2 3 B C A. So, these are positions. So, phase A takes the position 3. So, it is 3 3. Then A is connected to position A is connected to phase B, and then this phase B is in position 1. So, this is 3 1. Then phase C is connected to position 2. So, it is 3 2, and so on and so forth, right. So, I can say that this is equation 3. So, you see now equation 1 gives the relation between voltage and current for section 1. Equation 2 gives the relation between voltage and current between in section 2. Equation 3 gives the relation between voltage and current in section 3. So, then therefore, to find out the total voltage drop in the entire length of this line, we have to add these 3 voltages and then let us see what happens. So, then therefore, if I do add these 3 voltages, so adding these 3 voltages, so adding, so then adding 1, 2 and 3. Okay, before we add 1, 2, 3, let us first try to find out that what is meant by Z11. What is meant by Z11? So, then therefore, so first let us try to understand. Now, you see, if I say that my Zij is per unit length, if I say, if I define, let us define that Zij is, let us say that Zij is ijth element of the, let Zij of the impedance matrix this is per unit length. If I say, so then therefore, what would it be then? So, then therefore, what would it be Zijk? Zijk is the nothing but the element of the impedance matrix corresponding to the total length of section K. Now, what are the basically what are the length of the sections? For K is equal to 1, suppose if I say K and Sk. So, this for K is equal to 1 length is S1, for K is equal to 2 length is S2, for K is equal to 3 length is S3, right. So, then therefore, I can say that Zijk would be Sk into Zij, right, and of course, I and j would take the values, I and j will take the values 1, 2 and 3. These are corresponding to the positions, position 1, position 2, position 3, and Sk is the length of the lines, or rather length of the sections. Sk is the length of the sections. So, now with this, so then therefore, for example, I can say that, so then therefore, without writing it, so for example, I can say that Z111 and Z122 and etc., they would be nothing but S1 into Z11, S1 into Z12, S1 into Z13, S1 into Z21 and so on and so forth, right. So, all of them would be multiplied by S1. So, then therefore, I can say, so now adding, so now let us say that now adding equations 1, 2 and 3 together. Okay, now here for example, I can say the for example, say Z111 would be is equal to S1 into Z11, say Z, say Z 232 would be S2 into Z23, and say Z 3 Z say 313 is equal to S3 into Z31 similarly, right. So then therefore whenever there is the therefore for any section the total impedance can be found out by multiplying the per unit impedance element by the corresponding length of the line, right. So then therefore what I will get if I add equation 1, 2 and 3, so I would get VA, VB, VC. So that would be is equal to S1 into Z11 plus let us say S2 into Z22 plus S3 into Z33, and then it would be S1 into Z12, then S2 into Z23 into S3 into Z31, and then last one would be S1 into Z13 plus S2 into Z21 plus S3 into Z32. How we are getting it? For example, from the first one, how we are getting it? For example, for the first one, it will be Z11 1 plus Z222 plus Z333, and that is equal to nothing but S1 into Z11 plus S2 into Z22 plus S3 into Z333. For the 1 2 element, it would be Z121, so that means it would be S1 into Z12 plus Z232, so that means it is basically S2 into Z23 plus it is Z313 means S3 into Z31, and that's basically we are writing, right. I mean similarly this one. So then this one would be S1 into Z21, so S1 into Z21, it would be S1 into Z21 plus S2, it would be S2 into Z32 Z32 plus S3 into Z13 S3 into Z13, then it would be this one is S1 into Z22 S1 into Z22 plus S2 into I think Z33 Z33 plus S3 into Z11, then S1 into Z23 plus S2 into Z31 plus S3 into Z12, right. And then the last element is S1 into Z31 plus S2 into Z12 plus S3 into Z23, then S1 into Z32 plus S2 into Z13 plus S3 into Z21, Z21, and the last is S1 into Z33 plus S2 into Z11 plus S3 into Z22. So, this is the matrix, and this would be IA, IB, IC. Right. So, this would be IA, IB, IC. So, this is the matrix. Now, if these three conductors are same, so I can say that Z11 is equal to Z22 is equal to Z33, right. Now, is equal to say Zs, say. Now, what is the expressions of Zij? Now, just to understand this, that why this is true, Zij is equal to R A plus R D plus J omega k log dE by ds, right. This is ohm per say meter, this is for I is equal to J. R A is the basically resistance of the line and R D is the ground resistance, and this is equal to R D plus J omega k log dE by dij. This is for I not equal to j, right. So, these expressions we have already seen. So, then if these three conductors are identical, so then therefore, Ra would be same, and then of course, this value of ds would be same. So, then therefore, Z11 would be equal to Z22 would be equal to Z33 and it would be equal to Zs. And we have already seen that this impedance matrix is basically a symmetric matrix. So, then therefore, we know and also we know that Zij is equal to Zji, right. That also we know because this is a symmetric matrix. So, now therefore, what would be the diagonal elements of this matrix? Diagonal elements are or rather every diagonal element. Every diagonal element would be S1 plus S2 plus S3 into Zs, say it is S into Zs, right. So, that would be the all diagonal elements. So, each and every diagonal element is S into Zs because S1 plus S2 plus S3 is equal to S, right. And then what we have is that, and then we define that Zk1 is equal to S1 Z12 plus S2 Z23 plus S3 Z31, right. And then we define Zk2 is equal to S1 into Z13 plus S2 into Z21 plus S3 into Z32. So, you see that if I say that this is Z1, so then therefore, this is also Z1 because Z12 is equal to Z21, Z23 is equal to Z32 and Z31 is equal to Z13. So then therefore, I can say here, if this is ZK1, this is also ZK1, right? And if I say that this is S1 Z13 plus S2 Z21 plus S3 Z32, so therefore, if this is ZK2, if this is, I say that it is ZK2, I can say that this is also ZK2, right? And then I define also that ZK3 as, I define as ZK3 as S1 Z23, S1 Z23 plus S2 Z31 plus S3 Z12. If I say that, so then therefore S1 into Z23 is S1 into Z32, S2 into Z31 is S2 into Z13, and S3 into Z12 is S3 into Z12. So then therefore, if I say that this is ZK3, if I say that this is ZK3, if I say that this is ZK3, so this is also ZK3, right? So with this, now we can say that what is, so then therefore finally, my matrix becomes diagonal is S into ZS. Then I said that this is ZK1, then we said that this is ZK2, then we also proved that if this is ZK1, this is also ZK1. All diagonal elements, I said that this is SZS, and we said that this is ZK3, that we defined, actually defined, this is actually defined, this is also defined. So this is ZK3, and then this is, we said that this is ZK2, and then we said that this also would be ZK3. We have just now said this is ZK3, and this is SZS into I A B C. So you see here also all diagonal elements are going to be equal, right? And this matrix is also a symmetric matrix, right? So this matrix is also, even with transposition, theoretically we have shown that the final impedance matrix of the line would be a symmetric matrix, and if all these conductors are identical, all these diagonal elements also would be the same, right? So this, and of course usually that all these three conductors are identical, we always use. So then therefore with that practical situation in mind, so this matrix I can say that this is also a symmetric matrix, symmetric matrix. So this is the final impedance matrix of a transposed transmission line. So we stop this lecture here. In the next lecture we will look into an numerical example with these equations. Thank you.